What's up everybody, and welcome to a new part of my Coding a Decision Tree from Scratch series. In this part we're going to adjust our algorithm in such a way that we can also do a regression task with it. Therefore, let's first in this video understand on a theoretical level what we need to change about the algorithm, and then based on that in the next video we're going to implement the actual changes in the code. Okay, so let's first look at the flowchart of our algorithm again, and then also at the scatter plot depicting the iris flower dataset. When we applied this algorithm to this data, then we found those decision boundaries, and this was a classification task. And it was a classification task because the label that we want to predict was the species of the flower. So it was a categorical variable that could take on only 3 distinct classes. So now, obviously, to make or to do a regression task, we first need a label that is a continuous variable. And here I simply created such a label, namely a fictional price that we could sell the flowers for. And this price ranges between $0 and $10. So the darker the color of a dot, the higher the price that we could sell that flower for. And when you look at this plot, then you can see that there seem to be 2 distinct groups of flowers. In this cluster here on the left, the dots are brighter, so those flowers in general have a lower price. And the flowers here in this right cluster, those dots are darker, so those flowers generally have a higher price. So then accordingly, to be able to make good predictions about the price of new unknown flowers, the decision boundary then should ideally be between those 2 groups of flowers. For example, at a petal width of 0.8. Okay, so let's say that our algorithm has found this decision boundary. How do we now make predictions about new unknown flowers that fall into these areas? So what price are we going to predict for a flower that falls in the left area? And what price are we going to predict for a flower that falls into the right area? So in terms of our flowchart here, we are thinking about this classify step. And since we're now distinguishing between classification and regression, classify is probably not the best name for the step, so let's rename it to create leaf. And here, just as a side note, I think it is called leaf because along the analogy of a real tree, if you start at the root of the tree and then move along the tree, then the last thing that you will reach are the leaves. So that's why I think those places here where we make our predictions are called leaves. In the context of our decision boundaries here, we could probably also call the step create decision boundary, but we're going to stick with create leaf. Okay, so originally for the classification task, we created a leaf by simply checking which class appears most often in such a split area. For the regression task, however, we can't do this anymore because the flowers in such a split area, they all might have a different price. So they, so to say, belong all to a different class. So that's why we can then create a leaf by simply checking which class appears most often, because each class appears equally often. And even if there would be some flowers that happen to have the same price, that doesn't necessarily mean that they are representative for those flowers in general. So how do we then create a leaf when we are doing a regression task? Well, a simple approach would be to simply calculate the average price of all those flowers here and use that as the prediction for new unknown flowers that fall into that area. And that's exactly what we're going to do in our code. So the first thing that we need to change about the algorithm is how we create a leaf once we have found the best split to split the data. And this begs then obviously the question, how do we find the split here in the first place? Well, just like it was the case for the classification task, we first determine all the potential splits. And just as a side note, in the code update video of this playlist, we changed our get potential splits function in such a way that we would regard the actual values of the dots of the flowers as potential splits. But as you can see here, I have here depicted the splits again in between those values. And I simply did that because I think this way the plot looks cleaner when the lines are in between those dots instead of being right on those dots. And since that also doesn't change anything about the following explanations, I chose to do it this way. Okay, so now we need to be able to determine out of all those potential splits, we need to be able to determine which of those is the best split to split the data. And in the context of classification task, we then used a metric called entropy. And for that, I have a whole video where I explain how that works. So you can check that out if you want to. I will put the link to that into the description. But let me give you here just a quick recap of that. Namely, what the entropy measures is, so to say, the impurity of the data. So if you have two classes, then the entropy is going to be maximized or reaches maximum value when both classes have the same probability, so 0.5 in this case. And this maximum value for the entropy, so where each class has the same probability, gets higher and higher the more classes there are. So if you have 3 classes and each class has this probability of 1/3, then the maximum entropy is going to be 1.58 and so on. So if you wanted to summarize the behavior of the entropy, then what you could say is that the entropy, the more classes there are and the more evenly they are mixed up, the higher the entropy is going to be. Okay, so keeping that in mind, let's now think about what would happen if we would use the entropy to determine the best split when we are doing a regression task. Therefore, let's assume for now that all those flowers here have a different price. So as said before, they, so to say, all belong to a different class, and each class therefore has the same probability. So we are only looking at maximum entropy values. Okay, so now to understand how this entropy behaves for the different splits, let's look only at some edge cases of those splits. So we're going to look at those most outer splits here, and actually we're going to look at splits that are even one step further outside. In terms of best splitting the data, those splits don't really make any sense, but they will help us understand how the entropy behaves for different splits. And then we're going to look at one more edge case, and this is going to be this split here. And what's special about this one is that it cuts our data in half. So for this split, there's an equal number of dots on each side. Okay, so now let's start with this split here on the far left. Here, all of the flowers are on the right side of the split. So therefore, the entropy of the right side is going to be very high. So it's, in this case, 7.04. And on the left side of the split, there are 0 flowers, so the entropy is also going to be 0. And by the way, I will also upload the notebook where I created all those plots, so if you want to, you can also check out the calculations for yourself. Okay, so now, since the entropy only tells us something about one side of the split, we then calculate the overall entropy to get an understanding of the whole situation created by this split. And the overall entropy is simply a weighted average of those two entropy values. So since all the flowers are here on the right side of the split, the weight for the right side is going to be a 1 and the weight for the left side is going to be 0. So the overall entropy for this split is completely determined by the entropy of the right side, so it's also going to be 7.04. And the same kind of reasoning applies to the split on the far right. Only here, obviously, all the flowers are on the left side of the split. Okay, and now let's look at the split here in the middle. Here, as said before, there's an equal number of dots on each side. So the entropy on each side is going to be the same. It's 6.04 in this case. And since the overall entropy is just a weighted average of those two values, the overall entropy for this split is obviously also going to be 6.04. So now if we look at all the splits again, then we can see that the overall entropy is lowest for this split here in the middle. And this necessarily must be the case. And that's because for those outer splits here, the overall entropy is based on the entropy that you get when you have to consider all of the dots. Whereas for this middle split here, the overall entropy is basically just based on the entropy that you get for half of the dots, or when you have to consider half of the dots. So therefore, it consequently must be lower than the overall entropy of those outer splits. So if we then look again at our potential splits, what we should see is that if we start here at the far left and then move towards this split that cuts the data in half, we should see that the overall entropy keeps decreasing until we reach this point. And after that, when we move again away, it should increase again. And if we look at the actual values, that's exactly what we see. So here, the entropy is pretty high. Then it keeps decreasing until we reach the split that cuts the data in half. And then it keeps decreasing. And then again, when we move away, it keeps increasing again. So for this special case, where all the flowers have a different price, using the entropy to determine the split for a regression task results in the fact that the best split is simply the one that cuts the data in half. So it doesn't really detect any patterns in the data. And it simply cuts the data in half. And even if there would be some flowers that happen to have the same price, this wouldn't really change anything about the behavior of the entropy in general. We certainly wouldn't find that this split here is actually the best one. So clearly, we can't use the entropy for regression tasks to find the best split, and we need a different metric for that. So let's now think about what that metric should measure. So what it should tell us about the data. Namely, what it should tell us is something about how similar the flowers are to each other in such a split area. And it shouldn't measure if they are actually the same, like entropy does. And a metric that does exactly that is for example, the mean squared error. And for that, I also already have a whole video where I explain how that works. This, however, was done in the context of deep learning. So the formula that we are using here looks slightly different than the one that we used in the context of deep learning. But you can nevertheless watch that video to understand how the mean squared error generally works. And I will put the link to that again into the video description. But again, let me just give you a quick recap of that. Namely, what you do for this metric is from the actual value, so for example this one, you subtract the prediction. So in our case, the prediction then simply was the average price of all those flowers. And this is then the error, and this error then you simply square. And that calculation you simply do for all the examples I that you have. So for each dot here, you subtract the average price and then square that error. And then in the end, you simply calculate the mean of all those squared errors. Hence the name mean squared error. And then, just like we did with the entropy, we simply calculate the overall mean squared error, which is again just a weighted average of the mean squared errors of both sides. Okay, So that's the metric that we're going to use to determine the best split. So let's now think about how this metric behaves for different splits. And therefore, let's first look at this one. And here you can see that there are only dots with a generally high price, or only flowers with a generally high price on the right side. So the average price of all those flowers here is going to be a relatively good representation for those flowers in general. So none of those flowers here is going to be very far away from our prediction, so from the average. So therefore, the error is going to be relatively small for each of those dots. And therefore, obviously, then, of course, the mean squared error of the right side is also going to be relatively small. And the same kind of reasoning applies to the left side. Only here, obviously, there are only we only have flowers with a generally low price. So the mean squared error also is going to be relatively low. And therefore, obviously, of course, the overall mean squared error is also going to be relatively low for this split. And now, if we move, however, the split to the left, then we now have this flower with a generally low price in the right split area. So the average price of all those flowers here is now going to be somewhat lower. And therefore, all those flowers that have a generally high price are going to be a little bit further away from the average. So the errors are going to be a little bit bigger. Therefore then also we add the error of this flower here, which is going to be relatively big because it's far away from the average. So overall then, the mean squared error for this side is going to be a little bit higher than it was for this split. And on the left side, since there are still only flowers with a generally low price, the mean squared error is not really going to change compared to this one. So what happens when we move this split to the left is that the mean squared error of the right side increases and the mean squared error of the left side stays the same. So the overall mean squared error of this split is going to be then higher than it was for this one. And the same kind of thing happens when we move the split to the right. Only here, obviously, then the mean squared error of the left side increases and the mean squared error of the right side stays the same. So, as you can see, the mean squared error really tells us something about how similar the flowers are in such a split area. Namely, the lower it is, the more similar the flowers are to each other. And therefore, then we should find that this split here is actually the one that results in the lowest overall mean squared error because it separates those two groups of flowers. And if we now look at all the potential splits and their respective overall mean squared errors, we can see that this one is really the one that results in the lowest overall mean squared error. All the others have a higher value. So the second change that we need to do about the algorithm is how we determine the best split. Namely, instead of determining the one with the lowest overall entropy, we are going to determine the one with the lowest overall mean squared error. And now, just to make this flowchart a little bit more general and therefore applicable to both classification and regression, let's rename the step again to determine best split. And that's already it, what we need to change about the algorithm. Only those two steps. The other ones are going to stay the same. The potential splits function, are we going to determine the potential splits just as we did before. And we're also going to split the data as we did before. And we also don't have to change anything about this data pure function. Here we only have to keep in mind that it will probably never say that the data is pure when we're doing a regression task. And that's because the only cases where it would say that it is pure is when there's only one flower left, or maybe when just a couple of flowers happen to have the same price. In those cases, however, the decision tree would have many layers, and one of the other base cases would have been already applicable, namely either the max depth parameter of our algorithm or the min samples parameter. So again, therefore, to make this flowchart more general and applicable to classification and regression, let's rename the step to simply base cases. So if the base cases apply, then we're going to create a leaf. Okay, so that's everything we need to know about how we should adjust our algorithm. So now, therefore, let's look at the data that we're going to be working with. Namely, it's a data set about bike rentals, and I got it from Kaggle. So you can check out this site to know more about this data set. I will also put the link again into the description, but basically it just contains information about bike rentals of the years 2011 and 2012 in Washington, D.C. And some of the features that we have are time related. For example, the date, the month, if the date was a holiday or not, what weekday it was, and if it was a working day or not. And then we also have some weather related features. For example, the temperature, humidity, or wind speed. And here at the end, we have the count. So the number of bikes that were rented on that particular date. And this is our label. This is what we want to predict. So for any given day, we want to be able to say how many bikes are going to be rented for that day. So that's the data that we're going to be working with. And here I have created just some more time-related features. So what day of the year it is, what day of the month, if it is the end or start of the month, and so on. And here in this cell, I created a new column, which is called label. And that's because for our algorithm to work, the last column must contain the label and it must also be called label. And then the last thing that I prepared is the split or the creation of the training, validation, and test data sets. And since we are working now with a time series, I didn't create those by simply randomly picking from the data frame, but instead I simply picked the last 2 months of the data as our testing data set. So that's November and December of 2012. And the 2 months before that are our validation data set. So that's September and October of 2012. And everything before that is our training data. Okay, and with that now we are finished with all the preparations, so we can start to implement the actual changes in the code. And this will be the topic of the upcoming video. So thanks for watching, and hopefully I will see you in the next video.